Hello, welcome to my talk. It's called Large-Scale Data Analysis Using the App Engine Pipeline API. My name is Slatkin. I'm a software engineer on the Google App Engine team. These are the hashtags for this. And our feedback form, that's a 1. So 1, lowercase g, uppercase G, lowercase b, s. Couldn't possibly be any harder. Sure, I'll get some great feedback. Anyway, here are the two projects we're kind of talking about today, App Engine Pipeline and MapReduce, the MapReduce project. I also realized that it's kind of bad to put a 301 session as the last session of an entire conference, which is what this is. So there's a lot of code in this presentation, and I realize that might be very hard for you to read. So luckily, you all have tablets and other things to read things on. So this is linked to the slides that you're about to see. So if you want to follow along and can't read, it's Google P2U2S. So you can click on that or download that and check it out. It's a PDF. OK, so let's talk about kind of motivation for the Pipeline API. And then I'll kind of talk about what it is and all that. So there's something that people want to do that's very common. It's a data join. What is a data join? Basically, we're saying, I have a bunch of data, and I want to do a join on it, like an SQL join. I want to join two unrelated tables together into a single view. I want to combine data by the features that it has. And you want to do this for all kinds of reasons, the same reason you want to do an SQL join, because you want to generate views or reports or any kind of aggregate data or derivative data. So some examples of this is any kind of ranking, doing heat map diagrams, any kind of statistical roll-ups, stats, et cetera. And so since you know what you want to do, why you want to do it, when do you want to do it? I mean, you need to do a join when the data sources are kind of mismatched for what you're trying to accomplish. So each data set that you're trying to analyze or join has something else that it's optimized for. So logging is optimized for write latency. And then, especially with a high replication data store, a lot of things are optimized for per user views, not global views. So you want to join different data that's optimized for totally different uses to produce other outputs for a third use. So that's kind of what we're talking about when you'd really want to do a data join. Now, what makes this all unique from just a standard SQL join is that you have a lot of data. So you can't just do it in an SQL table with a simple join or an in-memory join. There's just too much information. So that's why I'm calling it data join. So I wanted to use like a real example for this. So I wanted to just give one that really I think everyone can relate to. I was going to do a contrived example, but I think this one's a little more solid. So it's a sales report. Okay, we've got simple data store kinds, tables. We've got sales, so what was sold to a customer. That's basically customers to items. So many-to-many table, pretty easy. We have the items, how much they cost. Item to cost, it's 1-to-1. And then we have categories of things. So what kind of thing is an item? So items have many categories. And so here's some example data in our fake business tables here. We have customers A, B, and C. We've got milkshakes, pies, and fries. We've got categories that these can belong to, desserts, food, or drinks. And then we have a price for each one. So a milkshake is both a dessert and a drink. It's not rocket science. But something you might want to do with this information is generate a report, right? So you've got customer. You want to know how much is each customer spending and what category is making you the most revenue. Very simple, like desirable thing. And most of you would say, well, this is really easy. I'll just do a join of an SQL table. And you may know that, well, I'll get to that in a second. So here's the SQL that would do this. So you have, if you want to do by customer, you just do a join of the sales table to the items table. And group by the customer ID. If you want to do it by category, you kind of have to do a triple join. I'm sure someone in the room knows how to do this with no joins in SQL. I'm just trying to emphasize that you need multiple joins usually to do this kind of thing. So you join categories to sales and sales to items, and then you sum up by the item price. The problem is that this eventually will break. At some point, you will get so much data in your data store that you cannot do these joins anymore. And so I think that it's so what we're talking about, and the way I'm trying to frame this is that you want this information, these aggregates, these roll-ups, And you want them to keep working forever, no matter how much data you have. So that's a big problem. And the solution that people usually say is, oh, MapReduce. I will just use MapReduce, and that will solve everything. It's like, throw some MapReduce on it. It's great. And that's true. It keeps working at extreme sizes. Ooh, that was a big diagram, huh? OK, so MapReduce is great. The problem is that MapReduce doesn't actually solve this. There's a whole bunch of different kinds of data analysis that you cannot do in a single MapReduce. So what you find is that people end up making MapReduces that are multiple stages or very deep. So they run one MapReduce, take the output of that into another MapReduce, and so on and so forth. Excuse me. So let me give you an example. Here's a diagram of when you might do this. So here's the same joins again, the roll-ups that I just told you about, as a series of MapReduces. So I'm going to step you through this, so don't worry. So in blue are maps. On the left, we have mapping categories, mapping items, mapping sales. So we map item IDs to categories, item IDs to prices, item IDs to customers. Then we do a shuffle and reduce to join them on the item ID. That basically collates them all by the item ID and aggregates them together. So then we have a mapping of item IDs to the categories, the costs, and a list of customer sales. Then we run a map on the output of that, and then invert those key value pairs. So then we output a list of categories to cost and customer IDs to cost. And then we shuffle and reduce that to collate or join on category and customer again. And at the end, it spits out the sum of all costs for each category or for each customer ID. Okay? There are more efficient ways to do this, but I'm just trying to illustrate the example here. I think that this is a common use case that you'll see. So that's great. You can solve this with MapReduces. Isn't that awesome? Wonderful. Well, there's a few things that are actually kind of difficult about this. It's mostly a solution, but now you have a new problem, which is how do you actually run all these MapReduces? If I asked you what to do with a lot of big data, you'd say, oh, I'll use Hadoop, I'll use MapReduce. But if I said, you have 5 MapReduces, connect them together, name a tool off the top of your head. Maybe people would say Uzi, which is the thing from Yahoo for Hadoop. But it's not like there's a common thing we all agree on for the go-to tool for this in the open source toolkit. So that's kind of the problem. And the reason is that Fannin is really hard. It's hard to make this work. And Fannin is this thing on the left. Mapping categories, mapping items, mapping sales, all separately, and then shuffling them together or joining them together. So that's fanning in. That's what we're trying to do. And it turns out that Fannin is actually just a type of workflow. So you're saying, do this, then that, or wait, do this thing, then wait for these 3 other things to finish. It's kind of a general problem. And so if you solve the general problem, I know workflow is a dirty word, but if you kind of solve the workflow problem in a simple way, it should solve the Fannin problem too. OK, so hopefully that makes sense. Are people with me so far? So great, OK. So I just want to talk about some workflow prior art really quickly. Workflow is like content management systems. It's a dirty word. It's like a terrible thing. Like, don't ever say, I have created the world's foremost workflow engine or content management system. Like, it's terrible. Sorry. And so I wanted to kind of just throw some mud or basically show you how I've been unhappy with the workflow tools out there. I'm not trying to create a generalized workflow platform. Don't worry. This is about data, and I'll get back to why. But I want to just kind of frame the context here a little bit. So the first one is finite state machines. So I have had a lot of experience building finite state machines at Google. I built a cluster management tool that I'll show you in a sec. The Append billing system is mostly a finite state machine. There's a lot of high performance flows throughout Google that are state machines. The problem is it's just this explosion of states. You've got deterministic behavior. You've got a small number of states in the beginning. And then what happens is every time you need to add a feature, you add more states. And you get this kind of like combinatorial explosion of behavior. It's really hard to work with somebody else on something that has kind of finite state machine semantics. It's hard to have an interface. It's hard to do reuse. It's very difficult to test. There's tons of examples out there. There's Phantasm for App Engine, which we have an article about. You should read about. I'm not trying to knock Phantasm in particular. For certain workloads, finite state machines are very good. But for the kind of thing I wanted to do, I don't think it's a good fit. Uzi is the other one that is kind of like a finite state machine. You describe, I swear, you describe your whole state machine in XML with like if statements and XML and stuff like that, and it's really verbose. This is the state diagram from my project that did cluster management. This is not my state diagram. This is the one I replaced. It's like 70 states. This deleted all of the error states and error transitions. And they're like, hey, maintain this. It's like, no, I'm not going to do that. Like, I'm going to replace it with something else, right? So, OK, yeah, so all right, keep going. So another one's work queues. This is very similar to App Engine queues, or Gearman, if you've heard of that. Producer style, consumer style queues, everything's a small chunk of kind of equal size or large, but equal size. The input and output's really well defined. The big thing here is that they're linear. Do A, then B, then C, then D, then E, always, or dump it in the error bucket. And I think that work queues work really well for that kind of stuff. I feel like you see that a lot. But there's really no control flow. If you need to branch off to a whole different set of logic, that's very difficult to do. And so it's hard to test the whole workflow from end to end if you need to try variations of kind of how to progress through the workflow. Another kind is data dependencies. We have a bunch of these at Google. Think about like make, the semantics of a make file, but instead of being CC files and .o files, it's input data and output data. And instead of running a compiler, you're running MapReduce for 8 hours. It's really cool, really, really cool. The coolest thing it can do is incremental builds. That's really cool. So you can say, OK, build this hard thing once a day, build these small things 100 times a day. And then with the final result, go spit out some other output data. So that's really cool. It's great for that. Zero control flow. It's like totally declarative. You can't have any outside input or intervention from a human. It has to be all files. You can only really test it as a black box, so inputs and outputs, just look at the data. We haven't open sourced any of these because they're so tightly coupled to their infrastructure, so I don't expect to see any of those out there. And then the last one is flow-oriented. So this is cascading. If you've ever used cascading, that's flow-oriented. So you convert your data into like this tuple-tuple space. You define transforms on the arbitrary tuples. It's awesome because it automatically optimizes your code by figuring out the graph of what you're doing in transforms, and then it'll merge certain operations and do all kinds of cool stuff. I think that this is really cool, but it's really complex, and you have to buy into the religion that is flow processing. And for most people, this isn't even useful until you get over a terabyte of data, so you don't even need to do it, right? And there's no glue. So you can't, at some point, you might just need to shell out and download a file or cat something or look at a list somewhere or like ping a server, like whatever. You need some kind of glue in order to do certain workflows. I think that's really important. So I think this is cool stuff, but I don't think it's quite right for what I want it to do. OK, so how the pipeline API is different. So basically, it took all kind of these different systems that are already there and to try to learn from them. And the other thing that kind of carried into this was thinking about functional languages like Erlang and Haskell. And so one of the coolest things about those, besides the fact that you have to use your brain differently in order to use them, is that they are parallelizable. So when someone says, I like functional programming, and you ask them why, and it's like, I like the style, it's like, yes, the style is cool. But the coolest reason is that you can just, when you do a fold or something like that, it can run on multiple machines. That's why it's cool. It's parallelizable. That's the point. It's a first-class part of the language. It's the fact that it can be optimized in ways you don't even understand. And that's really cool. So I wanted to see, can I carry over some of those ideas to languages I like to use? I don't think I'm smart enough to use Haskell. I've tried, cannot do it. I don't know. Maybe there'd be like a Haskell for Python programmers kind of tutorial I could read. That would be nice, but it's too hard. And so I wanted to carry those over to Python and Java and see what it could be like. I wanted to link back to the slides here, just in case, because now it's like a lot of code. So P2, U2S, if you want the slides. P2, U2S. So, OK, so here are my assumptions. I have a lot of threads. I've got extremely highly available storage, which is awesome. I've got elastic scaling of dynamic instances, so the queues will just spool them up. I've got apps with thousands of instances. And I don't have to configure anything. They just get spooled up, which is pretty crazy assumptions. And then my goals were kind of different than a lot of other kind of workflow or data-oriented engines. I didn't want to be deterministic specifically. Functional testing was a core part of what I wanted to be able to do. I wanted the components that you generate to be fully reusable so that multiple teams can actually build tools, like workflows that build on the same data. I want it to be productionized, so that's like having tools to look at the state of the process as it's running or to diagnose problems when things fail, to have back off and retry. And then I want it to be minimal. So what's the minimal number of tools I need in order to build this? Non-goals, static analysis. I'm not doing that. Automatic optimization, I don't want to do. I'm not trying to make a flow system. I'm not trying to create sustainable flow rates. And I don't want to use XML. I don't want BPEL in there. Yeah. OK, so the types of work I do want to do, so first of all, is synchronous work. So up until yesterday, up to 10 minutes was a task queue task. That was the limit. Now you can go as long as you want, as long as you have an instance around of a backend. So synchronous work is web service calls, doing a lot of transactions, any kind of iteration on the data store that takes a really long time. If you just want to write your code in a straight line, do it. That's the easiest and fastest and first way to do anything, so just do it. That's a great place to start. I want to be able to support that work and let that code run for a long time if you want to, you don't have to keep maintaining it or something. Then I also want to allow for asynchronous work. So fire off the work, wait for a callback, and then tie in with other frameworks to basically tell them to start and then have them call you back when they're done and then hook into the rest of the system like that. So MapReduce is a good example of this. It takes hours to run. If you want to send an email to a user. So this is a really simple one. We have exceptional things happen in production all the time. If the process had just told us, we would have been able to tell it, here's what you should do the right thing. But we don't even really have the tools to do that right now. So what I'd really like is if I could run a MapReduce and it's like, hey, I just hit a piece of data that's totally weird, there's something corrupted, or I don't know what to do here. If it could just email me with a yes or no and a description of what it saw, and I could just click yes, and then it would go back to work. That'd be awesome. Or I could go and look at the panel and say, oh, yes, OK, there's something wrong here. I'm going to diagnose the problem right now while it's paused. So that's that kind of asynchronous work is really important, too. And then webhooks, so post-commit hooks on Git or anything like that, I'd want to be able to interface with. But in the end, it's all about the coordination stuff. So I'm trying to build glue. I want to be able to pass arguments between different functions and pieces of work and take their outputs and pass them to other pieces of work. I want to be able to spawn a lot of different child tasks and wait for them. And in the end, I want to make joining really easy. So that first diagram I had with the maps on the left side, I want to make that process of combining data together really easy. OK, so let's talk about making Python and Java parallel. Maybe here's the slides. Yes, OK, that's where it is. So that's where they are. OK, so let's get into this. So I'm trying to define a subset of Python and a subset of Java that can be parallelized, but isn't wacky. So here's how it started. All right, so here's some Python. I have 3 pipelines here. The first one is add. Adds A and B, returns a value. Multiply, multiplies A and B, returns a value. But then this linear function here is actually a multi-stage pipeline that can be, well, this one can't be parallelized, but you'll see what's happening. So you may remember a linear function is y equals mx plus b. So here I'm saying yield, I'm using the Python yield statement, yield a new multiply child pipeline, give it the parameters x and slope, take mx, which is the future, it's a future value, take that future and then pass it to add, and then also add offset to there. Yield that job also, and then basically return the result. So this is really simple syntax, but what happens is that multiply and add can actually be scheduled to run in the future. They don't have to be run synchronously. So it looks like really simple code. It is, that's the point, right? It almost looks kind of stupid, but this style of just allowing you to pass features around lets you do some really powerful things, which is really cool. The other thing I wanted to do is make it really easy to invoke. So now that I have a linear function, I want to just pass it some parameters, call start, and then it'll give me back a handle to talk to this job later. And then later on, I can just say, hey, from this ID, give me back that object from before. Check to see if it's done. If it is, then I can hit the value and get the result. So I want to make it really, really easy to start and receive the output of these things. And then testing, I wanted testing to be a first-class thing. So there's two parts to this. The first part is on the bottom here. So start test. Because of the way we're defining pipelines, you can run them in serial. So you can use your Python debugger and just step through it. So if you have a problem, you can run in the whole pipeline in test mode, does all the things you think it should be doing, and then as soon as you get an exception stack trace, the call stack at that point will be how you actually got there through all of the sub-pipelines. I've never seen a workflow tool that can do that. That's really important to me because that's the kind of stuff I need to debug and then build new tests for. And then at the end, you can just grab the values here and make some assertions about how the pipeline ran. Further, though, sometimes pipelines take too long, or they have to hit external resources that aren't there. So you want to have built-in mocking facilities for that, which is what run test is. So run test is a special method that's also there that basically says, oh, when you run me in testing mode, just do this behavior. It's good enough of an approximation of the real thing for our purposes of testing, right? So for instance, in MapReduce, the mapper framework, when it has run test, it doesn't have to add tasks. It doesn't have to do any scheduling or quotas. It just takes the data, calls the map function on it synchronously, and then it returns the result. So you don't have to do all the work that you normally would do to test the thing. You can make a fake. OK, yeah. All right, so this is the same thing for Java. So I'm trying to be equal with my kind of focus here. The font size has to be smaller. What can I say? It is a little bit more verbose. I'm sorry, guys. But yeah, bulk it up. Yeah. But but I will say for Java, this is pretty pithy. So it's the same thing. Add and multiply. They return two immediate values, a plus b, a times b. And then we've got that linear function, which is computes mx, and then passes mx to the future call, adding mx plus b. That's it. And the invocation style is similar. You grab the service from the factory. You start a new pipeline with the simple parameters. Sometime later, you take that pipeline ID, grab the job info, look at the output, look at the status, see that it's done, look at the output. Really simple, right? Java does not have a functional testing piece yet, but that's something we're working on. It'll come soon. It'll work the same way, where you can step through the Java debugger to find where your code's not working the way it should. OK, so just to kind of clarify what we're doing here, I want to talk about kind of more of the specifics about how this thing works. So future values. What is a future? If you've ever done asynchronous programming or used twisted Python or anything like that, future values are kind of a weird thing to get your head around. And I think twisted Python programmers, they are constructed differently often. As programmers, they think about things very differently, much like functional programmers think about things differently. But I wanted the pipeline API to be really easy to understand and make it look like procedural code. But there are still restrictions. So feature values, when you call yield multiply and get back a result, you can't access it right now. You can't do that. It'll raise an exception. It'll say you can't do this. You can't grab the value, and there's no way to actually wait for it. So the function's not even there. It's not even defined. But what you can do is you can create another child that reads the result. So you can create a log value that will log a value that's passed to it, and then you can pass a future to that pipeline. So really simple idea. This one works. So essentially, anything that's passed into your run method, you can access. That's the gist of this. And this is what lets you do all these cool things. So again, immediate values, if you're passed it in your run method, then you can do anything you want with it. You can do comparisons. You can pass it to functions, whatever you want. It's just a value. But the key thing here is that when you pass values between different pipelines, so here I'm passing the output of multiply to log value. Multiply is going to run in one task, totally on its own, up to 10-minute deadline. And log value is going to run in its own task, totally separate for 10 minutes. they're totally separated from each other, and the pipeline API is coordinating the communication of the results between them. Okay? It looks like procedural code, but it's not. Java works the same way. You cannot access the value of a feature. It just doesn't work. So when you make a feature call, you can't call getValue. There's no such method. But you can take that value of the feature and pass it to another job like print it, which will then print the value. So it works exactly the same way. So just really simple semantics for how to deal with features. Java immediates work exactly the same way. The only difference is that you have to wrap them in this immediate little function wrapper or method wrapper. We'll probably make that shorter to like I or something, or M, or I don't know, sometime. But that's all it takes. So let's talk about why this works. This is hopefully will now clarify everything we've just been talking about. So here's a pipeline. I'm sorry if I'm giving you math flashbacks. Here's a polynomial function. You might remember ax squared plus bx plus c gives you some kind of polynomial of some variety. So I have add, which takes multiple values and sums them. I have multiply, which will multiply multiple values together. So this is kind of the same things from before. And now I have 3 child pipelines here. So ax equals yield multiply axx. Then I have bx equals yield multiply bx. Now what's really cool is I can run those in parallel. And the pipeline API will do that. So when you yield those 2 things, and it's like, oh, I have no data dependencies, it just runs them. And they run in 2 separate tasks with as much of a deadline as they can have. And then when they're done, they pass the results back. And then the add child gets kicked off, which took those results. And then it runs. So that's what I'm talking about, coordination in Fannin. So let's go through like a graphical version of this, because hopefully this will solidify what I'm talking about. So on the left are immediate values, A, B, X, and C. Okay? The green boxes are tasks. The blue slots are data that we're going to generate. And then we'll talk about the barrier. So straight away, once you say pipeline start, it's like, well, OK, I have immediate values on multiply. These guys are good to go. It schedules tasks. The tasks run. And when the tasks are done, they fill the slots. The task can run in any order. It doesn't matter. They can be idempotent. They might run multiple times. It doesn't matter. Those are the semantics of the API. And when each slot is filled, it'll notify the barrier. The barrier will wait for both slot A and B in any order to be done. Once they're both done, it'll notify add, and it'll say run. Add will then go find the parameters it needs, pull them in, slot A, B, and C, do what it needs to do, and then fill slot C. And then it'll call you back and basically say, I'm done. And now you can go grab the result of the polynomial. That's it. Does it make sense so far? People getting it? OK, cool. OK, so demo. I have a small demo of this. OK, so I have this. This is my favorite color guest book. This is a lot of data here. I know you came to see large-scale data analysis, so I did not fail to deliver here. So I've got like at least 500 colors in here that people like, I'm pretty sure. Anyway, so what you can do is you can add a color. So you know, orange or oh, there we go. Wireless is working. OK. Azure is a great color. I like that one. It's a really nice color. OK, so I'll run a reporting pipeline. And so this says, send me an email with a count of favorite colors. OK? So let's just do the basic kind. 3 colors we like. Blue. All right, so then you click run. And now this is going to redirect us to this UI. I'm going to turn off autopilot just so we don't overwhelm ourselves. OK, so what happens is the pipeline's now running, and this is the production interface. And if you went to Mike Ozatsky's talk on MapReduce, it's the same UI. The UI is generated from the call graph. You don't have to do anything. You just get the UI. We just figure it out from how your code works. That's the point. And same UI is used in Java and Python because it's all JavaScript. We just take the description of your graph and we render it. That's all there is to it. And then it's got a bunch of facilities in it. So the pipeline's going along here. I'll describe what it's doing. You can watch it as it goes. You can see that the current leftmost, newest pipeline is selected automatically. That's part of what it does. And so it'll progress, and we'll get into it. So the key things here, though, are that you see every substage that was created. You see how the parameters were passed between them. You see what the outputs were. You see who filled the outputs. If I go down here to a task, you don't really have to know what these are, but the point is, let me make these bigger, I'm sorry. So here's an append operation. Append is doing a fan out. It's a fan in. It's taking 3 different jobs and adding them all into one list, okay? And so here you can see the first value is filled by this long count operation. The second value is filled by this other one. And the third one is filled by this other one. And then append just mashed them all together, and then it output something here. So you can inspect your own call graph as it ran, and you'd be like, hey, why did this break? What happened? Why am I in retry or back off? And by default, the pipeline API will actually email you when something breaks. So you have to turn that off. And you can click around. So you'd be like, oh, long count, what did that do? And you click on it, and it goes there, and so on. So I'm going to run this again, if I can. Let's see, how many times do I need to push back? This is a bug, it's the back button. What can I say? Oh, you know what's good? It's just deleting the URL bar. OK, so try this again. I want to just highlight another part of this, which is the kind of production piece, which is when I run the pipeline, there's a pipeline here. You'll see it turns yellow. That's one that's in the retry state. I have one here that just automatically just raises an exception just to show what it looks like. So you'll see on the left here, it's a useless pipeline. And it's like, it just errored. And it's like, here's the exception string. So whoops, I need to retry is what it said. And it's retrying, and it says it will run in 14 seconds. And if you click here, it says it's going to run in 1 second. And then the second time around, it runs, and then it's done. And this is just all on the task queue in the background. Now, what this thing actually does, I can describe really quickly. What happens is there's a function that gets called split count. Split count says, I have these guestbook posts. They have an attribute called color. I want to know the counts for red and blue. So it'll go and it'll spit out 2 child pipelines that do long counts, that just basically do a query and just keep going, iterating until it gets to the end. And so they'll count up to 10,000 or for 10 minutes or as long as you want. With cursors, you can just keep going. So you can count as many objects as you want and do that report generation. And then finally, when long count's done, it's like, I have the answer. It says it's done. The output gets set out. And then it goes and tells all of its dependent pipelines. So here's append. Append waits for those 2, like I said before. And then at the very end, basically, there's an aggregation of all those reports across all these different tasks down into this email. And the email basically says, hey, here's Brett's email address. Send him an email with this report. We found 97 red and 130 blue. OK? So what this actually does is totally stupid. The point is that you have the tools to look at all of the different parameters, how they're passed, how much time they took, why they went into an error state, et cetera, et cetera. So it's a really nice debugging tool. You can also add consoles and links to every single job and a status message. So you can have a graph here of how things are going. And I think I have a word count demo. So here's like a more advanced. Let's see if that loads. If that loads, that'd be cool. Really? Oh, there it is. OK. So here's like this is like a hacked up word count pipeline I had from some other time. But what's cool here is you can see like, here's a shuffler. Oh, wait, that's not a good example. So here's like the mapper framework running inside the pipeline API. OK? So the point is that you can do all kinds of really cool stuff here, just creating consoles for yourself. And it just kind of builds the UI for you. You don't have to like worry about that. Oh, and it reloads and automatically, that's the autopilot feature. It reloads and automatically finds the next cool thing to look at. So it's pretty nice. That just comes for free. OK, so let's talk about a few more kind of details of what the pipeline API can do. And then we'll get back to our motivating example. So fan out, again, this is really simple. I want to send a bunch of emails to people. Sometimes emails take a long time to send, or you have to retry. So here I have an email invites pipeline. It takes an event ID. It goes to the data store, gets it. It goes through all the people who were invited, and then it sends an email to them. It yields a child for each one, for each to address, send them an email. Right? Pretty simple. The cool thing is that This code, email invites, will run linearly. It'll just run through. Every time you yield a child, that will get scheduled for running in the future. And then as soon as this finishes, all the children will start running. It'll just kick off. Fannin is also similarly interesting. So I have this great idea for a search engine. I want to take the word count of every link on the page, like what it links to, and that's how you determine the quality of the current page. So if you've got more links to content that's bigger, it's better. That's my like $1 million idea here. So I built the beginnings of this search engine. I have a new pipeline called the word count URL. It goes and fetches a URL, and it splits the data and counts how many words are on it, and then returns that value. So that's the top. That's synchronous. That could take 10 minutes, or maybe it'll take 30 minutes. Maybe you want to do some more interesting processing on it. It doesn't really matter. I've got a sum pipeline, which just adds up a bunch of values. And then I have my search engine pipeline. It says, hey, here's a bunch of URLs I found in this page. Please go fetch all of them, count up how many words are on each one, sum them together, and then return the result. So you do a for loop through the URLs. You yield a child pipeline for all of them. And then you sum the results of all the children. So this is a barrier on all the child pipelines. All of the different word count URL child pipelines, they'll all go out and run. And then once all of them have completed, all of the answers will be aggregated together and then handed to Sum. Sum will add them up and then say, here's the total, and then my pipeline will complete with the total. So that's Fannin. I mean, it's really simple. This shouldn't look like much because it's not, but you can do really powerful things just with that simple mechanism. Sequencing is another thing you need to do. So you want to say, run job A, then run job B, and once they're, after both of those, go clean up some files I accidentally wrote along the way. And then after that, update the dashboard and email the team. Sometimes you just want to do stuff in order. You don't have any data dependencies, so you have a way of describing that. We got the same stuff in Java, fan out. Send email is the same thing. You don't really have to look at it. Send invites, same thing again. I pass in a serializable invite object that's got some properties. It goes through, spawns a child for each one. That's all there is to it. This fans out. They all run immediately. It's great. And then same thing with Fannin. So with Fannin, I've got here I've got the word count URL and sum again. With Java, I got a few more things. I got to get some UTF-8 in there. I got to get some kind of like factories, but not so bad. I had to go on the next page. What can I say? But here again, you see I have a list of results. I call word count URL for each URL that I received, and then I take the list and I pass it to Sum, and I return that at the bottom. So Fannin is also very easy to describe in Java. Is it making sense so far to people also? Okay, cool. And sequencing on Java is exactly the same. You have another parameter. You can say wait for A. So you don't have to have data dependencies. You can just say do this after that. And then let's talk about asynchronous real quick. This is the silliest asynchronous pipeline you could make. It's just delay. Do something after 5 seconds, right? So all this does is when you run it, it says how many seconds to run for. It enqueues a task, a callback task, which is built into the system. It says countdown is seconds, call me back, and then it enqueues it. And the pipeline API has built-in routing to call you back on your actual object. It'll reconstruct the object for you and then dump you into kind of exactly the state you were in before and then run you right there. So when you get called here, self has all the different methods you're used to, and it feels like you're in the same pipeline again. So this is how we also execute the mapper framework in the pipeline API and so on. Anything that's asynchronous, you can run this way. Any toolkit you've already built that's asynchronous, you can run it this way. So this is how you connect to existing tools. It's just like, I'm going to run, schedule some stuff to happen, give that stuff a callback. It's opaque, just enqueue a task that looks like this. So whatever framework you're using can then enqueue that task. And when that framework's done, the task goes in, it calls me back, and then the callback function runs. And then it can figure out what it needs to do. It can move to the next state. You can do multiple callbacks for every asynchronous worker. It's totally up to you what you do here. So it's just, this is the kind of, the way to connect into other pieces. Java has the same thing. It's done a little differently. In Java, we actually have promises. So promises are like futures, but they're like futures from somebody else. So this is a promise that somebody else will fill this value. So in this example, I have something that I want to go find out everybody's favorite color. Okay? So I send them an email. I have their address. I send them an email. I said, hey, here's your token. And then with that token, I want to then save the color that somebody gave me. So see the bottom feature call, new saved color. So that's the piece that actually uses the promised value. And then what this means is that some other agent, some other framework, some web request handler, it doesn't matter, can call submit promised value anytime in the future using that token. As soon as it submits that value, the saved color pipeline will get kicked off. So it's all kind of event-driven based on data dependencies. And then finally, one before finally, there's finalized, which is sometimes you just got to do something when you're done. So MapReduce, you always got to delete files when you're done. So the pipeline API just has that built in. Finalized, map, shuffle, reduce, and then delete all the blobster files that were passed into this thing. So that's a primary feature of the system. And then finally, there's the production part, which is basically like you need to be able to abort a pipeline all the way to the root. You need to be able to retry a pipeline. You need to be able to set status. You need to be able to do it from the inside or from the outside. All these tools are there. So if you've ever dealt with workflows in production, these are the tools I've always wanted, and so they're all there for you to use. So language differences. So coming to Java, functional testing, some production optimization of the way that the entities are constructed, status links, integration with Mapper framework to make full MapReduce for Append in Java. Maybe we'll add finalized. Python has support for named return values. It's a pretty advanced feature. You can check it out. Probably won't add that. Java can serialize anything, which is cool. So Java has this edge where you can just pass all your classes around. In Python, you can only use JSONable types. Okay, so you can't pass raw objects through. You have to have something that can be serialized into JSON. Python probably won't add promises either, because that's just not really the style. So let's get back to this data join example. So this has been kind of a moving target over the last few weeks. So I'm going to, well, I'll get to it in a second. But so this is the big diagram I had in the beginning, if you remember. Again, we map category, item, and sales on the left. So those would be child pipelines that get run doing maps. The outputs of all those would then get joined into one shuffle, and then the shuffle output would be passed to a reduce. Then the reduce output would get passed to a map, and then the map would get passed to another shuffle and another reduce. Okay, so you can see the first part is really the join here. You can imagine other things being joined in at other parts along the way. Okay, so this is like the simplest graph I can make, but you can think of a lot of other kind of crazy graphs with a lot of other inputs. But so earlier today, Mike Izatsky pushed out, who's my colleague, pushed out the full MapReduce for App Engine. Using the Mapper framework and Pipeline API together. It's in the project. And I wanted to show you how you would describe this whole workflow using his system and using the Pipeline API. So the moving target thing I was talking about is that what the API that Mike's pushed out has been a moving target. So I do not have an example for you to run right now that runs this code. But I will very soon, and I'll get it out there so you can all run it. But I want to show you what the code looks like, just so you can understand the kinds of things that this is able to do. So here's the data join on the Pipeline API. So the first thing we need to do is the left part of this. Actually, I have this in red. Yeah. So this part. So mapping three things together, joining them, and then doing shuffle and reduce. That's like the first step. I want to do that part. So here's the Python code to describe that. I want to run 3 map pipelines. One for categories, one for items, and one for sales. The first map pipeline is going to call map categories on everything, reading from the data store of the category entity kind. The second one will call map items on the items data store kind. The third one will do map sales on the sales kind, pretty easy. And then I'll take the results of all 3, append them together, and then pass them to the shuffle pipeline. That will shuffle them all together, collate them by item ID. So this, I think it's 15 lines, describes the left side of this. There's obviously mapper code in there that's maybe 1 or 2 lines each to actually pull out the fields into tuples. But the point is, like, The hard part, in my opinion, which is connecting the pieces, is really simple. That's all it is. So once I've gotten that result, then I need the rest. So here's the whole sales report. I yield that pipeline I just told you. So join on the item ID, gives me back a feature of join data. Then I run reduce on that, reducing the items, output it to blob store as records. Then I run MapReduce on the output again, which inverts the pairs and then sums the values. So that's those two functions, using a record reader and the record output writer. And that's it. And then there's another feature in there for passing in the reduce output. So this is another 10, 15 lines to describe the second part, which is the map expansion and the shuffle reduction. And so through just about 25, 30 lines of code total, you can describe this whole pipeline through a series of data dependencies that are functionally described, procedurally described. So that's where we're going. So I'm going to have this example for you guys. I'm sorry I don't have it today, but this is what we're going to have as a demo of the pipeline API and to show you how big you can go. But I hope I've given you an idea of the kind of class of problems that we can solve using this API. And that's it. So if there are any questions, please come up to the mic. Yep.
I think it's fantastic.
Thanks.
My appreciations. And I think the syntax is a little bit more complicated when you compare it to functional programming. Functional programming has this idea of higher order functions where you can return a function as a return type and that executes. So that will take care of the pipelining problem. I know it's a hard problem for Java because you can't dynamically return the function, but probably it's at least for Python.
Yeah, I think we've thought of some ways to simplify, basically get rid of a lot of the wrapper syntax in the pipeline API. So you could add maybe you could add like an annotation to existing function and that would just work, or you could return a function that then is run. We want to do a lot of these things. There's kind of I consider that the sugar, so I agree that functional languages are shorter at describing a lot of this stuff. I think we'll be able to add some things to make it even shorter. So I agree with you, but that's why functional languages are the way they are, is so they can do all kinds of currying and other advanced stuff.
I think from a use case standpoint, it will help us a lot in terms of online reporting. So if you want to create different analytics with different sets of operators, you would want to create functions dynamically and pass it around.
Yeah, and that makes sense. And one of the things we've just talked about is maybe Java can serialize all kinds of really cool stuff that Python can't, like code. And so I think that we've talked about, under certain circumstances. So yeah, we're trying to make it even more dynamic to add, say like functions is a first class part of the API. But I don't think we're there yet. But it's definitely an interesting direction. I don't know how that'll turn out. So thanks. Yep. Hi,
you talked about where you were comparing with other things that exist inside Google and outside everything. The very common thing is like when you is the make kind of thing on data pipelines. So how does that fit in here? I didn't actually see if let's say I rerun a pipeline and there's pieces of the code of data that have been feeding into the pipeline that haven't changed.
Right.
Does it just? So
there's no incremental builds here. I think that's what you're asking. Yeah, there are no incremental builds. You'd have to build in your own logic into a child pipeline to say, oh, you wanted to run MapReduce here. I have a cache of those input values. Here's the last time I ran the output values. I think that it'd be very easy to add a cache like that to any existing pipeline, where it's just like, before you actually do this, check to see in some index, either in a data store or table or whatever, if, like a memoization function or something like that, have I run it in the last 15 minutes? If I have, just return the result I already computed. So I think you can add incremental builds to this, but you'd probably have to do it yourself. But I think that might be a cool thing we could add at the MapReduce framework layer, where the framework would understand. You could mark something as being an incremental build, say don't do this more than once every hour, and then have that carry through. So I think that's the direction we want to go in.
So for example, MapReduce does this automatically, for most cases, especially when it's things are failing and it's doing reruns and things.
You're saying like partial progress if you restart it and stuff like that.
Right.
Yeah, I think the MapReduce framework will do that too, to a point. What I think is interesting is more of running MapReduce like multiple times over the same day, over new data or variations of the data. And that's where I don't think the MapReduce frameworks, the MapReduce frameworks I've worked with don't do that part. Like MapReduce itself doesn't do that part. So you kind of have to add the incremental piece to it. So I think, yeah, I think it'd be a cool feature to add. So.
I know that you said you could get a stack trace if you get an error, but can you also trap the exception itself for production code?
Right. So if you get an error, so you're saying like a concurrency error, like I accidentally accessed this value or.
Well, let's say that you have a pipeline that goes off and fails for some reason. It needs to
okay. Yeah. No, in production you can't catch it. So it can run serially. So you have like child pipeline, parent pipeline, child pipeline, child pipeline. If this thing raises an exception, you don't get the exception back in the parent. I think that'd be a really cool thing to add. Functionally, or technically, that's difficult to implement for a lot of reasons. But so far, what happens is if the child dies for an exception, it'll retry if you ask it to. And if it retries too many times, it'll abort all the way to the root. And then it'll send this abort message to everybody to say, all right, something totally broke. Everybody stop what you're going to do. And then it emails the administrator with the status and a link to the page. But adding exceptional states would be cool. That's something we should do. Thanks. OK. All right, well, thanks a lot for coming. I know this is the last talk of the last day, so I appreciate you coming. I hope I have not hurt you too much. And thanks again.